Our next speaker is Gustavo Martin Bosyk from University of La Plata. His talk will be about majorization in quantum mechanics.
Okay, well, thank you. Well, I am going to talk about an application of majorization theory in quantum physics. This talk is based on this paper, which was done in collaboration with Federico Holick and Guido Bellomo. Okay. Well, what is majorization? Majorization is a mathematical tool that gives us a criterion to compare probability vectors in order to decide if one probability vector is more uncertain than other. Probability vectors. Yeah, probability distribution. Okay. From the very beginning, majorization is what developed in economy to compare income inequality of different populations. But nowadays, has several applications in different fields, in particular in quantum physics. Well, I start with the formal definition. Let us suppose we have two probability vectors, P and Q. The components are positive, and the sum is 1. This is the definition of the probability vector. And it is said that P is majored by Q, or Q majorizes P if we have these inequalities. This means that all the partial sum of the vector P are lower or equal all the partial sum of the vector Q. Here, the right arrow indicates that the components of P and Q are sorted in decreasing order. For example, this means that the greater component of P is lower or equal than the greater component of Q. The greater plus the second of these are lower or equal than the greater plus the second of this, and go on. So we have n minus 1 inequalities. An example, we have the more uncertain situation is the uniform distribution. We have all the probabilities are equal. Well, the uniform distribution is majorized by any other probability vectors. The other extreme case is when we have certainty. We have a vector with 1 and zeros. So the certainty vector majorizes any other probability vectors. Yes. The arrow indicates that the components of P and Q are sorted in decreasing order.
Oh, okay.
Yes, this is it. Okay? Yes, this is important. Well, majorization can be defined in an alternative way, which are related to two important concepts, the concept of double stochastic matrix and the concept of entropies. For example, it is said that P is majored by Q if I can write P as a multiplication of a double stochastic matrix by Q, or if this inequality is satisfied for all concave functions. This is related to the concept of entropy through the concept of short concave function. The short concave functions are functions that preserve the majorization order in this way. If P is majored by Q, then we have this relation between the functions. For example, all well-behaved entropy satisfies these conditions. Shannon entropy and another extension of Shannon entropy, like Sallis entropy or Renier entropy. It is important to remark that the concept of majorization, or to have a majorization relation, is stronger that say the entropy of this state is greater than the entropies of this one. Okay, it's a stronger condition. Well, from the other point of view, majorization is a lattice. That means the following. Let us consider this set of probability vectors, where the component, now I put explicitly, are sorted in decreasing order, the components of the vectors. Well, majorization gives a partial order because we have the reflexivity property, which means P is majored by P. We have antisymmetry property. If P is majorized by Q and Q is majored by P, then we have an equality. If I drop this condition, here appears a permutation matrix. R equal at least a permutation of the components. But I put this condition to have this property. And the last one is the transitivity. If P is majorized by Q and Q is majorized by R, this implies P is majorized by R. This is a partial order set. But as one expects, majorization is not total order because there exists incomparable vectors. This is an example. This vector is not majorized by Q, and Q is not majorized by P. Okay? But one can say a bit more about majorization from the order viewpoint. We have the infimum and the supremum. For all pair of vectors, there exists a unique infimum and supremum. For example, this means given P and Q, there exists a unique lower bound, a common lower bound, which is the greatest of all lower bound of P and Q. This is the infimum. And in the similar way, there exists the supremum of P and Q, given by majorization. Well, the set of probability vectors, the majorization relation, the infimum and supremum is called the majorization lattice, and this was shown for the first time in this paper in 2002, Chicales and Bancaro. Well, now the question is how majorization arises in quantum physics. Well, the quantum analog of probability vector are the density operators. So I talk about majorization between density matrix, in particular acting on a finite dimensional Hilbert space. The definition is the following. Rho is majorized by sigma if the vector formed by the eigenvalues of rho is majorized by the vector formed by the eigenvalues of sigma. This is the definition of majorization for density matrix. There is an important theorem that states this definition in the following way. It's the Ullmann theorem. It says rho is majorized by sigma if I can write rho as a convex combination of unitary transformation of sigma. Again, majorization between density matrix relates to quantum entropies. If I have a majorization relation, there exists sure concave function that preserve this order. And for example, the von Neumann entropy is a particular case. So this is the formal definition of majorization between density matrix. Now I will discuss a particular problem where this order between density matrices appears. Well, let us suppose we have Alice and Bob, and they share an initial entangled previous state, C, and the goal is to transform this state in another one by using local operations and classical communications. And the question is, which is the condition for this process of transformation to be possible? The answer to this question was posed in this paper, and it is known as Nielsen theorem. Well, these are the initial state, C, and this is the target state. I write the Smith decomposition of both states, and this is the vector formed by the Smith coefficient, the square of the Smith coefficient. These and these are probability vectors. Well, the Nielsen theorem says that C can be transformed to phi via log if and only if there exists a majorization relation between the reduced density matrix of the initial state and the reduced density matrix of the target state. Here appears a deep connection between entanglement transformation, non-local correlation, and local disorder. Local operation and classical communication. Yes. Well, we can write this condition in terms of the vector of the Smith coefficient. It's more easy to put this condition in terms of the probability vectors. Well, again, as is expected, the initial condition in general is not satisfied. This is an example. This state cannot be transformed to this one via lock, and this state cannot be transformed to this one via lock, because there is no majorization relation between these probability vectors. So let us suppose we have in this situation, I cannot go from the initial state to the target via lock. So what we can do? Well, there is another state that I can go. For example, this one, and there are infinite accessible states via lock from the initial. The question is, among all these states, which is the closest to the target one? This is the question. Well, this problem have addressed in this paper, and they pose a criterion. They obtain the optimum state in this way. Among all accessible states, they select or they choose the optimum as they want to maximize the fidelity between this accessible state and the target one, because the fidelity is a measure of closeness between two different quantum states. Higher fidelity, more closer the states are. Well, this problem can be posed instead of the state, instead of the probability vector. This is the ceiling, is equivalent. So here the key is using which is the measure of closeness between the states that we use. Vidal and collaboration use the fidelity. Now, our contribution was to ask if the lattice structure majorization plays some role or not in this problem. We define the supremum state in this way. This is an ad hoc definition. The supremum state is obtained via this Smith coefficient, where here appears the initial state, the target, and the supremum. And we show that there is a no trivial relation between the target state, the supremum, and the optimum one. We can order via majorization. Okay, this is a sketch of why this order exists. Suppose we have the trivial case. The trivial case, I can transform the initial into the target. Well, this is an initial theorem. This is initial, this is the target. So by definition, this is the supremum, and by definition, this is the optimum. This is the trivial case. Well, this is more interesting case is when I cannot transform this in this, but I have the opposite transformation allowed. In this case, the target is lower than the initial via the initial theorem. By definition, this is the supremum. Because the initial theorem, this is lower than this, and we have this chain. And again, we have this relation. But in the worst case, where both transformations are forbidden, we have implicitly three situations. The supremum and the optimum are not comparable via majorization. The optimum is lower than the supremum, or the supremum is lower than the optimum. We show in this paper that this is the only case. And we have this not trivial relation between the target, the supremum, and the optimum. But so far, there is no more than a mathematical curiosity. But we have this observation. Alpha, beta, and gamma are 2Q period states. And always for two-qubit period state, there is a relation, a majorization relation between the Smith coefficient. This always happens. And we have the intuition that the fidelity between this and this is greater than the fidelity between this, the last, and the first. So in this sense, the fidelity preserves the order. But what happens for higher dimension? This is an example. This is the initial state, this is target, this is the optimum, and this is the fidelity between the target and the optimum. This is the supremum state, and this is the fidelity between the target and the supremum. And we have, by definition of optimum, the fidelity between the target and the optimum is always greater than the fidelity between the target and the supremum. But because our theorem, we have this order relation. So in this case, we see that the fidelity does not respect this order relation. Okay? So in general, we see that the fidelity does not respect the majorization order. So now we measure of closeness respect this order. So we introduce this measure of distance that is formed by the sum of the Shannon entropy of P and Q minus twice the Shannon entropy of the supremum. This is the true distance in the majorization lattice because it's positive, it's symmetric, satisfies the triangle inequality, and more important for us, is compatible with the lattice. If we have this relation via majorization, the distance is computed via this formula, as is one expected. So using this distance, we can reinterpret our supremum state in this way. The supremum state now is, among all accessible states, is the one that minimizes the distance between the targets. And we show that the supremum state has more entanglement entropy than the optimum. So using this distance, we have reinterpreted the supremum state. So to summarize, we have addressed the problems of approximate entanglement transformation by using local operation and classical communication. We investigate the role of the lattice structure in this problem. We found that there is a not trivial relation between the target, the supremum, and the optimum states. In general, we have that the supremum and the optimum are different, but for certain particular cases, they are equal. In the case of two qubits, or when the target state is the maximal entanglement one. Well, this is a work, our first work. There are another interesting problems that maybe the lattice structure plays some role. For example, there are another entanglement transformation. This is known as entanglement assisted transformation. Suppose we can transform this in this via log, but by using an extra resource, C, this is entanglement state, we can do the transformation. Well, it's like a catalytic state because it's not consuming this entanglement. This log transformation induces a new partial order that is called trample majorization. There is an interesting open question if this new partial order has or not a lattice structure. Or majorization appears in another interesting problem. And here there is a nice paper where they look for this lattice structure in the error of time in classical and quantum thermodynamics. That's all.
Question about quantum topos. Naive question. I just wondered if this majorization is anything like Dar's ionization in that approach, because it seemed analogous to me, but I don't know.
Like
Dar's ionization is where you have this functor which takes you to a kind of maximal determination, right? So that everything is assigned yes or no. And it seems similar to this majorization where you move from probabilities to ones and zeros. If you don't know what I'm talking about, just move on.
Okay. Okay.
No, it has nothing to do, in principle. Maybe
Okay.
But because the
It's
lattice
different.
here is not the lattice of propositions
On a quantum system, it's the lattice of majorization, which is very different. It's not the von Neumann quantum lattice. So the Dasonization this shift that you mentioned is based on the context of a quantum state. This is not that lattice. It's very different, and it relates to different physical
Yes,
problems.
it's a lattice between probability vectors.
Just a question, because I wanted to be sure if I understood you
Yes.
correctly. First, you use fidelity.
Yes,
Then you realize that fidelity doesn't preserve order.
exactly,
And then you change it, notion of distance.
exactly, yes.
Okay. The notion of fidelity usually is good in quantum
Yes.
computation. And your notion of distance is also good. I mean, it's somehow performing well for estimating distances between states, especially having in mind quantum computation.
No, I don't know.
You don't know.
No,
Okay,
it's the
fine,
first
no.
time that we use this distance.
Yeah.
It's not my distance, it's the distance of Chicales and
Yeah,
Baccaro.
yeah, okay, sure,
that
sure.
appeared in another context,
Yeah.
but it's the first time that we use the distance. Because for me and Federico, it's something weird. We have an order, and we are using a measure that does not respect this order.
Yeah.
I know the fidelity is a good measure of
Yeah,
closeness.
but it's not the only estimator. You're
But
right.
it's
There
not-
are many
yes,
others.
the-
Yeah.
it's-
I wanted to know whether this new estimator they're using is also somehow useful.
This is the first application of majorization lattice in quantum information.
Yeah.
Our paper is the first application.
Yeah, no, I understood that.
So,
was the side
but
question.
now appears in this year, this paper, this paper discuss another application.
Okay, thank you.
Just sort of trying to understand the landscape of results. So these results are for bipartitions, right? I mean, like the results, specifically where you're talking about entanglement, we're always talking about a bipartite split.
Yes.
Just, do there exist in the world of results multi-partite results about entanglement?
I don't know if this multipart relate to majorization or not.
Okay.
I think not.
Okay. Because I'm always looking for a nice way to characterize whether a multipartite position, a partition of your system, right, not necessarily into particles, but maybe into degrees of freedom. I'm always looking for a nice way to put some sort of structure on the sets of possible observables. And so I would love it if, so you don't think there's any. Do you think it's profitable to think about it, or do you think it is not profitable?
What do you think that is possible?
We think that it's possible because if you only look at this from this point of view, you are only looking at the problem of log transformations and entanglement, but you can shift the description. If you go to this Corsequa paper,
Okay.
he looks at the problem in a different way.
Okay.
He uses to study the arrow of time, like a thermodynamic arrow, right? Which are in the end is a kind of resource theory. But we are trying to apply this to that approach and trying to see which is the mathematical underlying structure here. So there's a bundle. It's a kind of, you have the points here, which is the lattice, and the fibers. And the fibers, it turns out that they have a lot of geometrical structure. And here you have a structure related to entanglement that you could apply to multipartite. But of course, it's a work in progress. We don't have it published.
Well, we are perfect to go to lunch. Thank you.